All right, in this video, I'm going to continue to cover 7.4, so moment estimator and then maximum likelihood estimator. So um, let me second. So last time I introduced the moment estimator, I mean method of moments, so 7.4.1, right? So 7.4 excuse me, the method of estimation. So I'm going to introduce three methods for finding point estimator, right? So first one is method of moment, and the second one is method of maximum likelihood, and the third one is Bayesian estimator. So the we are doing a method of moment. So the key point is this: we're gonna construct the equation uh, by finding the the kth population moment and the kth sample moment. So, okay, equating kth population moment and kth sampling moment, and then we solve the equation for the uh, the uh, the parameter, uh, the population parameter. Okay, so then the right hand side, we can in the right hand side of the equation, we're gonna get the point estimator of the population parameter. So we see. Let me repeat what we did last time. So we know the moment, right? So the kth population moment. I mean, by the way, x1 through xn be random samples. Okay, sample data and sample. Okay, so and then the PMF PDF. I mean, f of x is a PMF or PDF depending on problems. And then kth population moment or distribution moment, you can say that's the expected value to of the x to the kth power. The corresponding case sample moment is 1 over n times sigma of xi to the case power. So here xi, x1 through xn are what random samples. Okay. So now I told you the idea of the method of moment is what equate population moment to the corresponding sample moment. So the first population moment going to be E of x. This is nothing but population what the population mean, right? And then the first sample moment, that's going to be a population, a sample mean. Okay. So now you say that we equating u and x bar. It means that u equals x bar. That it means that x bar going to be a moment estimator of the population parameter, population mean mu. Okay, so we can say mu hat. Mu hat is the notation of the point estimator, right, of the population mean, right? So we denote the population, point estimator of the population mean, mu hat, right? So now we can say that mu hat equals x bar, okay, which is the moment estimator. So then moment estimator, so let x1 through the xn be a random sample from either PD or PMF. Then f, this is the, I mean, f, right? F of theta 1 to theta m. Theta 1 to theta m are unknown parameters. I mean, these are the population parameters. Okay, so normally in this subject we only consider the up to two or three population parameters, population mean and then variance, or sometimes standard deviations, population standard deviations. So anyway, so the moment estimators denoted by theta 1 hat through theta m hat are found by equating the first m population moments to the first m sample moment and solving the resulting equation for the unknown parameters. So we saw example 7.6, right? Exponential distribution was this. Exponential random variable describe the length until the first event is obtained in a Poisson process. Okay, so and the Poisson process means the random variable x in the Poisson process is the distance between successive event from a Poisson process with a mean number of events lambda per unit interval. Okay. So now the give me a second. Yeah. So now the f of x is yeah. So since this is exponential distribution, right? So f of x is defined as lambda times e to the negative lambda x, and we know that mu, which is 1 over lambda. Okay, so in the first population moment going to be 1 over lambda. The first sample moment going to be x bar. So 1 over lambda equals x bar. It means that lambda is 1 over x bar. So 1 over x bar is the moment estimator of the population, um, the parameter lambda. Okay, so and then let's see. Give me a second. Let's see example. Then see so example. Let's suppose something. See, page 162 textbook. Okay, let's see page 162 textbook. All right. So in this textbook, you see, as an example, suppose that the time to failure of electronic module used in an automobile engine controller is tested at an elevated temperature to accelerate the failure mechanism. So the time to failure is exponentially distributed. Okay, so now we can use the result in the example 7.6. So 8 units are randomly selected and tested, resulting in the following failure time, x1 through x8. And these are random samples, right? Random samples, yes. And then we can find out the x bar, right? Sample mean. So we're gonna find the sum of all the values of random sample divided by number of the sample random samples, which is 8, right? So then we can find out the x bar, which is 21.65. Then moment estimator of lambda going to be, right, lambda head. That's going to be 1 over x bar, which is 1 over 21.65, which is 0.0462. Okay, so that's the application of the point estimator of the exponential distribution. Okay, so let me go back to the lecture note. All right, so see example 7.7. So normal distribution. So suppose the x1 through xn is a random sample from normal distribution, okay, with a parameter mu and a sigma square. So for the normal distribution, so I covered this one, right, in the last time, in the last lecture video. So let me go over again quickly. Okay, so now the first population, the moment is what, the mu, and the first sample moment is x bar. Right? Then now we're gonna find out the second population moment and the second sample moment. Okay, so the second population moment gonna be e of x squared, which is mu squared plus sigma squared, because sigma squared is what, e of x squared minus mu squared. That's why we got this. And then the second sample moment gonna be 1 over n times sigma xi squared. Okay, so now we equating mu equals x squared, and then give me a second. Say mu equals x squared, and then mu squared plus sigma squared, which is the second population moment, is equal to second sample moment. Right? So now we got the actually this kind of system of equation for mu and sigma. Okay, so keep in mind is we want to find the point estimator, moment estimator of mu and sigma. Okay, so we don't know mu and sigma, so that's a problem, right? So from here, the first equation, we figured out what moment estimator of mu, which is x bar. Okay, we'll see. Okay, and then the thing is this, the moment estimator of the sigma. Okay, so from here we replace the mu by mu square by mu square, and then sigma square by sigma square, and then the goal is to find out mu sigma square. Okay, so we're gonna isolate sigma square in this equation. Okay, so now then we got the doing some algebra, so we're gonna get this. So right there, where's one? We get this one sigma right there. So we got sigma and the xi minus x bar squared over n, right? Okay. So, but that's the sigma different from the what sample variance, right? So sample variance must be a sigma xi minus x bar squared over n minus 1, not n. So, so the moment estimator of sigma squared is not an unbiased estimator. I mean biased estimator. Okay. So now, okay, now we move to example 7.8 gamma distribution. So, okay, suppose x1 through xn is a random sample from a gamma distribution with a parameter r and lambda. Okay, so now for the gamma distribution, e of x is r of lambda, and the e of x squared is r times r plus 1 over lambda squared. So, if you don't remember what gamma distribution, please go back to the chapter what chapter 4. Okay, so please look at it. So in the chapter 4, we calculate, we figured out e of x and e of x squared. So now gamma random variable is the length until r events occurs in a Poisson process. Okay, so the exponential distribution is what? The random variable x in the exponential distribution is the length until first event occurred, right? And the gamma distribution is r event. Okay, this is more general case, right? So now the R of lambda is x bar. So where R of lambda comes from, this is the first population moment, right? And then x bar, yeah, this is the first sample moment. So guess what? The from we in this equation, what the population, the two parameters are involved, R and lambda, right? And then we're gonna construct the equation using the second population moment and the second sample moment. So left hand side. And here, the left is r times r plus 1 over lambda squared. This is what? That's the second population moment. And then right hand side is second sample moment. Okay. So now we got the two equations, right? R over lambda equals x bar, and then this equation. So these two equations are a system of equation for r and lambda. Okay. So now, so we're gonna find the moment estimator of lambda and r and lambda. I mean r hat, lambda hat. Okay. So here, so in the first equations, we solved the equation for r. So we got r equals lambda x. Now we're gonna plug in lambda x bar into what? Into the r. Okay, it's just algebra. Okay, so the so solving that system of equations by substituting x lambda times x bar into r in the second equations. Okay, then we gonna get this. Where's one? We figured out lambda is x bar over 1 over n times sigma xi squared minus x bar squared. So that's going to be a moment estimator of lambda, I mean lambda hat. Okay. And then once we figured out once we find the moment estimator of lambda, which is lambda hat, we're going to plug in this one into here, right here. Okay. So we figured out r equals lambda times x bar, right? So yeah, replacing r by r hat and then lambda by lambda hat, that we got this, and plug in this one into lambda hat, we get this. But that's the moment estimator of r, which is r hat. Okay. So okay, next one. Excuse me. Let's see another example. Okay, specific example. So the yeah, we sell this one, right? Excuse me. So yeah, I covered this one in a textbook, right? So let me skip it. By the way, so the here, let's see, second. Yeah, so it's a little bit different than the example what we covered in a textbook. Let's see, as an example, suppose the time to failure of an electronic module used in an automobile engine controller is tested at an elevated temperature to accelerate the failure mechanism. So the time to failure is exponential distribution. 8 units are randomly selected and tested, and then resulting in the following failure time. So yeah, so I think we the same random samples are given. Okay, as the textbook. So now we found the X bar, right, 21.65, and then we're gonna find our second sample moment. Okay, so this is 6645.43, and divide by what, the n, which is 8. That's gonna be second sample moment, right? So now anyway, so using this information, we can find out what moment estimator R and moment estimator lambda. I mean R hat and lambda hat. Okay, just applying those to the formula of the moment estimator lambda and R and lambda, we can figure out the R hat lambda hat. So let's see, what does that mean? This number 1.29 and the 0.0598. So when R equals 1, the gamma reduced to the exponential distribution. Yeah, so gamma, I told you what the exponential distribution is, the random the variable represent the what this what let's see, the on the measure the distance until the first the event occur, right? But gamma distribution is more general than the exponential distribution, not just one. R could be one or two, any number of the events. So the when R equals 1, the gamma reduces the to the exponential distribution. Because R has slightly exceeded 1, it is quite possible that either the gamma or exponential distribution would provide a reasonable the model for the data. So since 1.29, I know this is not, maybe you can say 1.29 is not pretty much close to 1, but the approximately 1.29 is, I mean, if you use it round, then we're gonna get 1, right? So so that's what, so what, in this example, we can use either gamma distribution or exponential distribution. Okay, either one just fine, because R hat is approximately 1. So that's interpretations. So now in the 7.4.2 method of maximum likelihood. Okay, so I'm gonna briefly introduce this one. Okay, and then uh, the just uh, I'll just cover this one in the next video. Okay, so method of maximum likelihood is one of the best method of obtaining a point estimator of parameter. Yeah, this is really popular. So let's see the method of maximum likelihood. Okay, so the estimator is the value of the parameter that maximizes the likelihood function. So what's the likelihood function? So I think we need to figure out likelihood define likelihood functions, okay? And then we want to try to find the maximum of the function. Okay, how can you find the maximum function? Remember that in a calculus, one, even the rarity maximum, rarity minimum, absolute maximum, absolute minimum. Okay, we're gonna use that technique. Okay, so see. First one, maximum likelihood estimator, MLE. So suppose X is a random variable with a PDF app. You see the X and the colon theta. So X is a random variable and theta means a parameter. Okay. So we assume that the function f, I mean, the PDF app is involved the single unknown population parameter. Okay. All right. So now x1 through xn be observed values. I mean, sample data. Okay. Definitely these are random sample. Okay. So random x1 through xn are random variables, and the x1 through xn, the group of x set of x1 xn, is called the random sample, okay, of size n. Then the likelihood function of the sample is this f of x1 colon theta times, you see that the product of all of the PDF replaced x by what, xi, okay, x1 through xn. Okay, there is the likelihood functions. So now I told you x1 through xn in a random sample, x1 through xn are considered as a random variable, right? So we just replace x by x1 through xn. So now you see that what likelihood, that was definition of a likelihood function, right? Definition of likelihood function is the product of the PDF. Okay, so PDF function replace the x by the random variable in a random sample. So the likelihood function is a function of only theta. You see, eventually, I mean, eventually x1 through xn will be given, right? It is a specific number in the problems. So the likelihood function must be what has only theta as the unknown variable, right? Okay, so actually likelihood function is a function of theta. But what's a theta? Parameter. Okay, so now the MLE, the maximum likelihood estimator of theta, is the value of theta that maximize the L of theta. Okay, so now we see example Bernoulli distribution MLE. Okay, so in a Bernoulli distribution, the PDF is defined as P of x times 1 minus P to the 1 minus x. We haven't seen this one, right? Actually, this is what the what was the binomial distribution, right? We haven't seen this one is a but not exactly, binomial distribution, but similar to the binomial distribution, right? So we only think about the one cases, right? So one, the event, okay? So now, the x can be 0 or 1, okay? What does that mean, 0? What does it mean, x? What does it mean, x? X is the what? Number of the success, actually, right? 0 or 1. We only think about just 1 or 0. 0 success, 1 success, okay? Where P is the parameter to be estimated. Okay, so now then LOP, let's find the LOP. That's going to be P of x1 times 1 minus P times 1 minus x to the first power, x of 1. This is f of what? x1 colon P, right? The second bracket is represent what? F of x2 colon P, right? You see that? This is f of x1 colon P. This is f of x2 colon P through the what? This is f of xn colon P, right? So now then, the protein, the product all of terms bracket, we're gonna get this. Because you see, look at this, P of x1 times P of x2 times through the P of xn. Since these exponential have the same base, we can combine them. So we got this P of sigma of xi. And the same, goes to 1 minus P. 1 minus P to the n minus sigma xi, right? Okay. So now we observe that if P hat maximizes LP, then P hat also maximizes ln of LP. So to find out the maximum to find out P maximize LLP, but here let me use a P hat because we know that the value of P maximize LLP, that's gonna be what maximum likelihood estimator. So we use a P hat. Okay. So now then, to find out P hat maximize LOP, that P hat will also maximize natural log of LOP because natural log LOP is an increasing function. Okay. So now, a second. Now, the take natural log into LLP, we're gonna get this. Right. So now then, we find out relative maximum using the first derivative test. Okay, what's the first derivative test? Yeah, just look at the CAC plus 1. Okay, so we're gonna find out the critical value, right? Okay, so now we find the critical value. To find the critical value, we have to take a derivative of natural log LOP with respect to P. Okay, then we're gonna do this. This is the the implicit differentiation of the natural log of LOP with respect to P. Okay, So now then, so we give a second. So now, okay. So we solve the what? The this one is equal to 0. Okay, see, you see the right hand side. Okay, that's the derivative of natural log L of p with respect p, and then we're gonna set this one equals 0 because we want to find out p where natural log L of p, I mean derivative of natural log L of p equals 0. That's gonna be critical value, right? So now then, the solving that equation, we solve this equation, okay? All right. So now then, yeah, it's okay. So first one, we make all these fractions is just we're gonna what we need to get rid of the denominator, right? So this is just doing applying a little bit of algebra, okay? So we're gonna get this, okay, and then the now we see sigma xi p and the sigma xi minus p right there. Just cancel them out. So we got this p is equal to 1 over n sigma xi. This, see that here? 1 over n times sigma xi. This is nothing but what? A simple mean, right? Okay. So maximum likely estimator of p is what? Actually simple mean. Okay. And then now, yeah, so how do you know that this is a maximum likelihood estimator? Yeah, we need to prove that, right? So once we've got the critical value, see that 1 over n times sigma xi, this is critical value. Keep in mind is x1 to xn are what? The sample data, okay, which are given, okay? So now using the including the decreasing test to check that the p is the what? The critical, I mean, the what? The maximum likelihood function has the maximum value at p. Okay, so we use the increasing decreasing function, increasing decreasing test. Okay, so now we pick the what? A second. Let's see. We plug in what? The what we to choose test a point on the we just divide the what number line. Okay, so remember that how to do this. So here, this is the what? The critical value right there. Okay, so we divide the number line into two survey number. Okay, right here, and then the first survey number, second survey number, and then we pick the test point for each survey numbers. Okay, and then we evaluate the natural log of LOP at those two test points to check the sign of, I mean, sorry, derivative of natural log of LOP. Okay, to check the sign of the derivative. Okay, so if you see that in at P1 derivative is greater than 0 and the P2 is derivative is less than 0. Okay, you can choose any number. Right? So it means that what the I mean, so how can you find the P1, P2? Because even xi are not given. Yeah, so um, when you see a specific example, you have to do this. Okay, I just explained the uh, the strategy. How can you do that? Okay, keep in mind this. So now, mm, you figured out that what the p, I mean, maximum likelihood function has maximum value at p. Okay. So once we figure out that, okay, so now we move on. So we can say that P at maximum likelihood estimator P is nothing but what? Sample mean. Okay. So I'll continue to the next example. Okay. The next video. Okay. So please, yeah, a lot of algebra is here. I just skip, right? So then you need to go over step by step by yourself. Okay. So do not just watch the this video. Okay. You just get a couple of sketch papers and then try to do by yourself. Okay. So you need to be familiar with maximum likelihood estimator. Okay, method of the moment, method of the maximum likelihood estimate. You need to be familiar. Okay. So once I just cover the 7.4 and 7.5, then I'm going to cover we'll see a couple of the online homework problems. Okay. All right. That's for today.